All right, I was asked to do something like one of these. And then I did get a question over the weekend, and somebody asked me if when you're doing a division of complex numbers, if you can get a result that isn't complex in the sense that it doesn't have an I in it. And the answer is that's absolutely possible. So if you get an answer and it doesn't have I, that doesn't necessarily mean that you did it wrong. Just an FYI. Um, the idea that comes into play when you're doing not long division, but if you're doing division with complex numbers, the idea that comes into play is the idea of the complex conjugate. And all a conjugate is with complex numbers is everything is the same except whatever the operator is in there, you write the opposite operator. So A minus BI is the conjugate of A plus BI and vice versa. So the conjugate of A minus BI is A plus BI. And the idea of conjugates are important in complex number world because if you multiply a complex number by its conjugate, you always get a number that isn't complex in the sense that the I term is a zero. So if you just multiply this out and you get A times A, and then you get A times the minus BI, which would give us minus ABI, and then you take the BI term here and you multiply it by the A, which would give you a plus ABI, and then multiply here, BI times minus BI, you get minus B times B is B squared, and I times I is I squared. And then this simplifies, and what you notice is that these middle terms are opposite and they cancel out and give you a zero. And whoops, and I did A times A is supposed to be A squared, and I said it but didn't write it. So you wind up getting the A squared minus the B squared. And then what we need to remember is that I is defined to be the square root of -1. So if you square the I, you're going to square a square root, which means that I squared is always equal to -1. So you can replace the I squared with -1, and then the negatives combine right here, and you get A squared plus B squared. And this turns out to just be a number, a real number on the real number line, and the I piece has gone away. So you could actually if you're multiplying a number by its conjugate and you actually have numbers sitting there like -2 minus 3i, and you wrote the conjugate and you took a product, you could actually shortcut the whole multiplication process because you're always going to get the A squared. So -2 times -2 is 4. You're always going to get a plus, and it's always going to be whatever B is squared. And in this case, B is a 3, so you'd get 3 squared is 9. So you can actually, because this middle always cancels, and you're always going to get a minus combining with the -1 from the I squared, you can shortcut. And what most people do once they get comfortable with it is they go from here to here because they know this cancelization is going to happen every time. They know that the -1 from the I squared is going to combine to give a plus every time, and you're just going to get A squared plus B squared. So I won't shortcut the multiplication process, but most people, once they're comfortable with conjugates, that's what they do. They just skip straight from this step to this step, understanding that how this is going to play out. So if we take a specific example, I don't want to do the ones on the practice test because I want to leave them for you guys to work on and show me pictures and remind, hopefully, because the last test was a nightmare. I had to curve the grades on it. Pretty hard, actually. So the idea is when you're doing a multiplication, you want to take advantage of this fact that if you multiply a complex number by its conjugate, that you get a real number. You want to take advantage of this to get the denominator converted into a real number. So the way that you do that is you multiply the denominator times its complex conjugate. So I go -3, and the 4i stay the same. And then I see the operator is a plus, so I'm going to write a minus. And what this is going to do is change the denominator from a complex number into a real number that has 0 for the complex part. But I can't just arbitrarily multiply something by something without having it get changed. So what I need to do is make sure I'm multiplying by 1, because if you multiply by 1, right, if you multiply something by 1, here I have a half. If I multiply it by 1, 5/5 is a funky form of 1. What do I get? I get 5/10. It looks the same, but it's still a half. Right? 5/10 of a pizza is the same as half a pizza. So we can multiply by funky forms of the number 1, which will always change how things look, but the result, even though it doesn't look like the original, is equivalent to the original. So up here, I want to get a real number in the denominator, so I'm going to multiply by the conjugate to make that happen. But I have to multiply by 1 or I change the value of this ratio. And all I want to do is change how it looks, not its value. And so once you get this set up, you just multiply out and simplify. You get the -2 times the -3 is a 6. The -2 times the -4i is going to be negative times negative is positive. And it's going to be 2 times 4 is 8i. And so I multiplied -2 by everything over in the parentheses. Now I'm going to multiply the -3i times everything in parentheses. So I get -3 times -3 is positive 9i. And then over here, I'm going to get the -3 times the -4, which is going to give me plus 16. But I also get an I times an I, which is an I squared. And this is going to be all over. And I'm going to, even though I know I could shortcut this, I'm just going to multiply it out. -3 times -3. It's going to give me positive 9. -3 times -4i. I get negative times negative is positive. 3 times 4 is 12, and it has an I in it. -3 times -4i is plus 12i. And then here I move on to the plus 4. Plus 4 times -3 is minus 12i. And then plus 4i times minus 4i is going to be minus 16i squared. And then just like we saw over here, the a times b plus the minus ab plus ab canceled. That happens right. Here's that canceling of the middle pieces happening, just like it does in the generic case. So if we bring it down and continue to simplify, we get 6. And I can combine the i's because they're like terms. So I have 8 i's plus 9 i's is plus 17 i's. And then I get plus 16 times, but I squared is just -1. We want to remember that I squared is -1, so I can replace that. And then the denominator, I get my 9. These two cancel and give me 0. You get the minus 16, and then the I squared is a -1, so I'm showing way more detail than what I think is necessary. And then up here, you're going to get, what, 6, and then the plus and the minus are going to combine, so it's going to be 6 minus 16.
Isn't the top one a 12i squared?
12
or am I missing that?
Right here, yep, it is, right there. -3 times 4.
Okay.
Is a 12i squared, which is going to change that to, thank you, 12, makes that a 12. And then that's going to be 6 minus 12, which is a -6, plus the 17i all over. And now you can see that denominator doesn't have an I in it anymore. It's just going to simplify to a 25. And that was the goal, was to get that denominator. as a real number, because what you want is to get this division completed, you want to get this written so that it's in standard form for complex numbers. You're trying to get it in that a plus bi form. And now we can do that because I have two terms in the numerator over a 25, so I can step over here and break it into the two fractions. I get a negative 6 over 25 plus my plus operator there, and then the 17 over 25, and it's times the I. So now I'm in that standard A plus BI form, which is what you're shooting for. So again, the idea is these intermediate steps we could have skipped. We could have looked at this and gone, hey, I'm multiplying by the conjugate in the denominator. So it's going to be negative 3 squared is 9 plus 4 squared is 16 is 25. Could have just gone straight to it by understanding that the middle stuff dies and these always combine to give you that plus. Is that okay?
So you're saying that we can skip all of it without showing all of the work and still get full credit?
Yeah, I mean the whole point of multiplying by the conjugate is so that you can get you want people to see the pattern and then understand that you don't have to show that work every time if you feel comfortable not showing it. It is okay to just say, I know how it turns out. In fact, I'm doing it to get a real number in the denominator. I am multiplying by the conjugate for only one purpose, to get a denominator that was complex into a real number form so that I can break it apart into that A plus BI format. Okay, and then the other one was completing the square. It's everybody's nemesis. Notice it's going to be the most heavily weighted problem on the next exam. So that should tell you how much I value this particular skill, especially in the context of a pre-calculus class, because there are some students who will go on to take trigonometry and calculus, and completing the square is used extensively in both of those classes. You can't get through them without being able to do it. So it would make sense to weight it heavily enough so that people who can't do it can't pass the class and move on into trig or calculus. So it is going to be weighted heavily in that sense. So the idea behind completing the square and the way that I do it isn't the only way to do it correctly. It's the way that I like to do it. I like to get the constant term over on the other side. You don't have to do that. There are ways to do it without doing that. But my first step would be to add that 10 to both sides to get that 10 out of my hair, because the completing the square is going to happen on the other side of the equation. And then you want to get all of the x stuff together. So I would subtract this x off of both sides so that the x stuff was on the left and the constant terms were on the right. And that would be my first move. Again, not the only way to do it, and you can find YouTube videos where people work the process through a little bit differently by getting it equal to 0 and just keeping everything on the left. I don't do it that way. And then the next thing is you have to recall that when we developed the completing the square process, that it was predicated on the leading coefficient, the coefficient of the x squared term. That leading coefficient needs to be a 1. The whole process of completing the square was predicated on that. So the next step is to get your 1, and you do that by dividing everything on the left by the leading coefficient, and whatever you do on the right-hand side, you have to do on the left. Whatever you do on one side, you have to do on the other. So if I divide everything on the left by 3, I've just made everything 3 times smaller on the left. The two sides won't be equal anymore unless I make the other side 3 times smaller as well. That's what division by 3 does. It makes sense, right? If you divide 6 by 3, it becomes 2. It's 3 times smaller than it was to begin with. So you're shrinking both sides by the same amount, because if you don't shrink them by the same amount, you cannot say that they're equal in the same way anymore. So you get them shrunk down, you get the x squared minus, and x over 3, we want to recognize that x over 3 means the same thing as 1/3 of an x. So you can write it like 1/3 x if you prefer to visualize it that way. It's the same thing. And then the completing the square, what we did when we developed the idea was we said we're going to take this middle coefficient, the coefficient on the linear term. The linear term is the x to the first term. We're going to grab him, and we have to keep the sign with him. So it's a negative 1/3. You grab him, you have him, and once he's halved, you square him. So a half of negative 1/3 is negative 1/6. Hold on a second. I'm just looking to make sure. No, we're fine. Oh, that's what I'm doing. I'm doing the one that I put on the practice test. I'm like, I know I trial ran through this earlier. I'm just gonna finish it now. Oh well. It's like that wasn't coming out like that. I put a number there because I wanted it to be a little bit more complicated. Oh well. And you keep, he's getting squared, and then you square him. So we get what, 1/36? And then you add that quantity to both sides to complete the square. So adding the 1/36 is what completes the area of a square on the left-hand side. And then the next step is who got squared? Who got squared? It should be, this is the guy that you squared right here. He has to go in there, and you have to have the negative with them as the operator. So it's x minus 1/6. And then here we would need a common denominator. So what would we get out of that? 121/36. And you could check your work on this. You either completed the square correctly here, or you didn't complete the square correctly here. So what you want to understand is if you take the x minus 1/6 out and square it, x minus 1/6 times x minus 1/6, you should get x times x is x squared minus 1/6 x minus 1/6 x. There's the minus 1/6 coming out of there. And then it would be minus minus plus, and 1/6 times 1/6 is 1/36. Then when you add these two guys right here together, x squared plus minus 2/6 x plus 1/36. 2/6 reduces to 1/3. You got to get this back. You completed a squaring is what it's called this because you've completed a squaring. So if you do this squaring, you need to get back the squaring that you completed. Remember when we developed this in the videos, what we talked about was that you always get this term twice and it adds up to something. So you're really getting whatever that is, you get 2 times 1/6 because you get it twice. And so to figure out what got squared up here, you have to have it to figure out the number that got squared, because you wind up getting 2 of them in the middle all the time. That's why you have it, because it's half of whatever it added up to that got squared. So you could check your work, and if you square it out and you don't get back the previous line, you know that you made a mistake somewhere. And then the idea behind completing the square is you can then use the square root property. And the square root property is predicated on the variable only showing up inside of a squaring. Because if the variable that you're trying to solve for shows up inside of a squaring, you can cancel the squaring by taking the square root. So the completing the square process is purposively trying to get you into a squared form so you can use the square root to dig the variable out. And then you got to remember to put the plus or minus. So the squaring, the square root cancels the squaring. And then you've got to simplify this. So you're going to get plus or minus the square root of 121 is 11 and the square root of 36 is 6. And then you add your 1/6 to both sides. And then if you can, you keep going. So we get 1 minus 11 is negative 10 over 6, comma, and then we get 1 plus 11 is 12 over 6. There's the two numbers popping out, and then simplify if you can. That negative 5/3 and 2. So it's kind of procedurally the same every time. Get the constant stuff on the right, get the x stuff on the left, generate a leading coefficient of 1, have the linear coefficient, and then square it. Add that amount to both sides. Rewrite it in a form that lets you solve it using the square root property. Is that okay?
Can you go through the one that you were originally going to do?
Sure.
I was working on that one while you were doing that one, and I'm just trying to see if
I thought
following.
I set that one up to be a complex answer, which is what I wanted something
Looks like
more,
it is.
Yeah, I wanted something more complicated. Let me. So I had wrote one that came out as a complex answers for the result. Plus 10 equals 3x. So if I did this one, same process, I'd subtract the 10 from both sides, and then I would subtract the 3x from both sides to try to get the constant terms on one side. And the x terms on the other. And then I want to check leading coefficient isn't 1. So divide everything by 2. That should be a negative 10. Simplify everything that you can. So here I've got a negative 5. And here I have an x squared minus 3/2 of an x. Leading coefficient is 1 now, so I'm going to take the coefficient on the linear term and halve it. And after I've halved it, I'm going to square it to complete the square. So I get a negative 3/4 is going to get squared. And when I square it, I'm going to get a 9/16. And I'm going to add that 9/16 to both sides. So on the left-hand side, I have completed the square. There should be something squared that gives me this summation on the left, and it should be x, and it's going to be minus the 3/4. It's going to be the thing that got squared going in here. And then here I would need a common denominator, so I'd be multiplying by 16 over 16, and 5 times 16 is 50 plus 30 is 80. So that's negative 80 plus 9 is negative 71 over 16. And now I have it in a form that allows me to use the square root property. The thing that I want to solve for is inside of a parentheses that's being squared, and it doesn't show up anyplace else. It's the only place it shows up, which means I can take the square root to kill the squaring, but if I do something on one side, I do it on the other, and I need a plus or minus on this because there's going to be two numbers that I can square to get what I want. We got it. The key is to remember the square root, by definition, is a positive number. So the square root of 4 is 2. That's what it is. It isn't plus or minus 2. It's just 2. But when you have an equation like x squared equals 4, that is something different. That's asking you what number, when you square it, will give you a 4. So if I do the square root of both sides, and the square root of 4 is just 2, that's all it is, it's only positive 2, I lose something that when squared will give me a 4, because it's also true that if I square a negative 2, I get a positive 4 as well. So the square root property is just that property that says, hey, yeah, the square root of 4 is a positive 2, but the opposite of whatever number comes out of here also works if you square it. So that's why you do the plus or minus. The square root would only give you a positive result. So when we're solving an equation, and I only bring this up because sometimes I see people working through and they're not in an equation, and I'll see people throw a plus or minus on. And so there's this misunderstanding that just because you took a square root of a number, you need to put a plus or minus, and that's not the case. So the square root cancels the squaring. And then I need to put this in simplified radical form. So the square root of 71 isn't going to simplify, but the denominator, the square root of 16, does simplify. And then the square root of negative 1 is an I, so I can just pull an I out of there. And then I would add the 3/4 to both sides. And that's going to be plus or minus the square root of 71 over the 4 times the I, and that's as far as that will go. Previous example, we kept going because we had two fractions that we could add and subtract, so we did it. Here, that's not going to be the case, so we just stop. And I think Alex made you feed it in as a comma separated list. So I think Alex made you input it like this: 3/4 plus the square root of 71 over 4i, comma, and then you had to write the other one. But in math world, it's more common when you have a plus or minus-y type of situation just to do a plus or minus. And in fact, when you look in at like at equation editors, they always give you the option to include that symbol. So this was the other one I was asked about, was solving using the square root property. So here's one that's like it. I made it a little bit more complicated than the one that's there, but not, it's essentially the same problem. And the square root property, this is one where on the exam, if you square this out and then use some other technique, you get a 0. So the square root property, you need to recognize when you can use it. The variable I want to solve for is only showing up in one place inside of something that's being squared, which means I'm going to be able to use the square root to dig it out. I don't need to multiply this whole thing out. In fact, I would be working harder than I needed to by multiplying that out. If there was another x floating around someplace, I would not be able to use the square root property. And in fact, I would need to multiply this all out and combine like terms and then use some other technique, factor by grouping, complete the square, quadratic formula. So if x showed up any place outside of the squaring, I couldn't ask you to use the square root property. Wouldn't be able to ask that. So here what you're needing to recognize is, hey, if I add 24 to both sides, the thing that I want will be sitting isolated being squared, which means I can dig them out by taking the square root of both sides. And I need a plus or minus. So the square root cancels the squaring. So you see, it's exactly the situation we were in with completing the square. Exactly the situation that we got. That's what, that completing the square process, that's what you're trying to get to, is that position where the square root property allows you to attack it. And then we want to simplify this if we can. So 24 is the same as 4 times 6. So I know there's a perfect square in a 24. So I'm going to add this 5 to both sides, which will leave me at 2x. And then I'll have a 5 plus or minus the square root of 4 is 2. And the square root of 6 is the square root of 6. It's already in simplified radical form. So I simplified this. And then I would need to just simply divide both sides by 2 at this point. So I get x equals 5 plus or minus 2 root 6 all over the 2. And you could break it into the 2 fractions, but it's not a complex number. So there's you could do this. It would be legit. 5 over the 2 plus or minus 2 square root of 6 over the 2. Legit to do that. And in fact, then this simplifies right here. But there's no requirement to write this in any particular form. So leaving it at this step would be perfectly fine in an exam setting. To report the answer in ALEKS, you would have had to bring it all the way down and then separate it into the 2 answers. And that's all I got, because that's all I was asked to do.
Thank you.
Yeah, the exam, if you want to know how it went interesting. It was a bloodbath. The highest grade on the exam was a 98%.
Was that with the curve?
No, this is pre-curve. So there were like 4 people who did really well. And the low score on the exam was about 4%. And then there was everything in between, with over 50% of the students had a score that would have generated an F. So
wow.
So what I did, the average score, the mean average, where you take all this exam scores, add them up, and divide by how many exams there are, was probably 62% was the mean average. So what I did was I actually used a linear equation. So I said, I'm going to map 98 to 100. So if you have 100%, that means you had the highest score and your actual score was a 98. And then I decided what to map this to. So I decided to map this. I mean, this is an F. I still mapped it to a score that's an F, but I mapped it to a much higher F. And then from that, I make a linear equation in the form y equals mx plus b. And then based on that linear equation, I plug everybody's percent in. And so like if you get a 40%, I plug the 40 in and it outputs a percent that's higher than the one that you had. So what this did is it took these D's and it probably mapped them up, depending on, it mapped them anywhere from a C to a C plus B minus, depending on how big the D was. So it mapped the D's up. So it's not an actual it's not an actual bell curve. It's just another method of scaling grades on an exam. The things that people couldn't do, handle fractions, that was across the board, which is not a good sign in a pre-calc class, because in calc, we've got to be able to deal with, we just have to be able to deal with fractions. In fact, in calculus, we don't get to use radical signs anymore. So things like the square root of x, we don't get to do that. We have to write our exponents in rational form. So our exponents have to be fractions. So if we can't handle, like, you can't do calculus unless your exponents are in this form. So you've got to be able to handle the fractions to get through calc. So I'm going to keep feeding them to you in the exams in the hopes that we improve our skill set in that arena. All right. Anything else before we get out of here?
Is it this recorded and going to be posted on Remind?
Yeah, it is. I'm going to post it.
Okay.
Yep. It'll take
All right,
a little bit, but it'll be in there in a bit.
Thanks. Have a good one.